Hi everyone, my name is Peter. Welcome to this YouTube tutorial. Today we are going to be looking at Organic Chemistry 1, and our topic today is going to be the SN reactions of ethers. So in one of my last YouTube videos that I made about alcohols, I showed you guys how alcohols have a poor leaving OH group. So this is the base structure of an alcohol. So alcohols have a poor leaving OH group because it's more basic, or it's a good nucleophile. It's a very strong nucleophile. So this strong nucleophile, this OH group, cannot easily be displaced by weak nucleophiles like the chloride ion, the iodine, and bromide ion. So therefore, what we have to do is we have to make this group a beta leaving group. And one of the ways that we saw was that to protonate this alcohol, when the alcohol is protonated, it becomes a beta leaving group, and we can displace it with any other weak or strong nucleophile. So ethers also behave as alcohols. The general structure of alcohols of ethers is this. So therefore, this group and this OH group have almost the same basicity. So alcohols have a pKa of about 15.7 and ethers have a pKa of about 15.5. So therefore, basically they are within the same range, and they both form very strong nucleophiles. So therefore, in the same way how we did the alcohol, is the same way how ethers are going to be treated. So therefore, let us see how can we make this group a beta leaving group so that ethers undergo a substitution nucleophilic reactions. So therefore, to begin with an example, first of all, the points to note. So the points to note here is that first of all, we are going to see what are those reasons that make alcohols or ethers beta leaving group, and what should we look out for when we are given a problem, and to see what is the major product. So therefore, we shall first look at the carbocation. Carbocation stability, that's number one. And also the other thing that we look for is steric hindrance. So these are the two major important things you look at when you're given a problem to find the major product in substitution reactions of both alcohols and ethers. So since you have this point in head now, so let us do an example. For example, if we have this type of molecule, so if I have this type of ether and I want to protonate this ether to form a beta leaving group, so if I have hydrogen bromide, so remember, bromine is more electronegative than hydrogen, so it will have more electrons towards itself than hydrogen. And we have a lone pair of electrons on oxygen, so therefore these lone pairs are going to attract this partially positive hydrogen, and this bond breaks off in favor of the bromide. Then we form something like this. So now we have formed a beta leaving group with the oxygen having a plus charge, meaning that oxygen is overloaded, or this molecule is unstable. So at this point, what happens is that if we break off this bond, once you have to ask yourself, do I form a stable carbocation? That's the first question. Then the second question is that, is there any steric hindrance when the bromine is going to bind on this? So therefore, when I break off this bond, I'm going to have something like this. I'm going to have this species like that, and methanol. So I've formed a tertiary carbocation. So this is more stable. So therefore, my bromide ion can easily attack this carbon. Then we have our final product as so this is 2-bromo, methyl propane. So this is my final product. So now you've seen how I've formed this major product by following carbocation stability. So therefore, in this SN reaction, we followed the SN1 mechanism because we formed a stable carbocation. So let us see how SN2 reactions will be when ethers react. So in an SN2 reaction, so we shall have so imagine I have this is methoxypropane. So if I have this methoxypropane and I'm reacting it with hydrogen, let me say hydrogen iodide. Remember, iodide is more electronegative than hydrogen, so we shall have these bonds, partial positive, partial negative. Oxygen has a lone pair of electron, so these lone pairs of electron are going to attack this hydrogen. So when the hydrogen is attacked, this bond breaks off in favor of bromine, and we shall have the following product, intermediate, the CH3 or CH2, CH2, CH3 with a hydrogen and a positive charge on the what? On the oxygen. So now here this previously was SN1. We saw that this bond breaks off. I don't know in favor of what. So if we break off this bond in favor of that, are we going to form a stable carbocation? Are we going to, is the resultant molecule, is it going to be, is there any steric hindrance? So now, so let us first look at the stability of the carbocation. So now, if this carbon gets a positive, it's already a primary carbocation. The same applies to this carbon. So therefore, both will form primary what? Carbocations. So therefore, carbocations is stability is out of the way because they both form the same. So now let us look at steric hindrance. Remember, we have this iodide ion coming in. So now this iodide ion will have what we call steric hindrance, where there's many carbon atoms. So now we see that we cannot form this hydrogen cannot attack this carbon because this carbon has steric hindrance. If you don't understand steric hindrance, I did a YouTube video on steric hindrance. You can check under my YouTube videos and you see the meaning of steric hindrance. So therefore, if this iodine ion bonds to this carbon, there will be steric hindrance. So what happens is that this bond breaks off in favor of that, and then this iodine attacks this carbon. Because this carbon, there's less steric hindrance. So we shall form this product plus propanol. So propanol and iodomethane are my major product. So I think you've seen how I've played around with the steric hindrance and stability of carbocations to come up with the major products. So you're going to encounter so many problems in organic chemistry, and the only thing that you have to reason is the stability of the carbocation and also steric hindrance. So thank you very much for watching this video. See you next time as we discuss further more organic chemistry. Bye for now.